in this theorem, we show that when we have a sequence in a metric space X that converges to a point P, every neighborhood of P contains most of the sequence, okay? Contains the numbers Pn, the points of the sequence, except for maybe some finally many of those, okay? So here it's very important to keep in mind that this finite number of points that are left out of the neighborhood, it may be like 1 trillion points of the sequence, but that's nothing compared to the infinitely many numbers that you have in the sequence. So, okay, remember the sequence is countable, so no matter how big the number of points you leave out, you will always have most of the sequence inside the neighborhood. All right, so to prove this, notice that we have an if and only if. So we have the two directions. Let's show first, assuming that Pn converges to P. Then let's show that every neighborhood of P contains most of the sequence. So for that, we need to say, well, okay, let V be a neighborhood of P. Okay, this means that now we need to show that this neighborhood contains most of the sequence. Now, for some epsilon positive, we have the condition that the distance between Q and P less than epsilon Q in X implies that Q is in V. This is by the definition of neighborhood. Now, once we have this, corresponding to this epsilon, okay, remember the definition of convergence. For every epsilon, there exists a number capital N such that for all n bigger or equal than capital N, we have that the distance between Pn and P is less than epsilon. Okay, so that means that if n is bigger or equal than n, Pn belongs to V. And that's what we wanted to show. Okay, this is saying that the Pn up to that number capital N may be outside of V, but then from capital N onwards, all of them are inside. Now, the other direction, if every neighborhood of P contains Pn for all but infinitely many n, okay, then Pn converges to P. So how do we show that? Now, suppose that every neighborhood of P contains all but finitely many Pn. Okay, and then fix some epsilon and let V be the set of points Q in X, the points in the metric space that are within a distance epsilon of P, okay, of the limit P. Now, by assumption, because we have said that for every neighborhood of P, it contains Pn for all but finally many n, okay, we can say that by assumption there exists some number n, capital N, that corresponds to V, such that Pn belongs to V if n is bigger or equal than n. Okay, this means that the distance between Pn and P is less than epsilon if n bigger or equal than capital epsilon. And that is the definition of convergence from Pn to P. So we are done here.